This talk really connects very well to the talk of Luca that you have just seen. And I will tell you about molecular dynamics in general and more specific about ab initio molecular dynamics and a little bit more than that you'll see in the end of the talk. And I'll start by telling you why, turning it on, why we actually perform molecular dynamics, okay? So as you've seen in the talk of Luca, I mean, when you want to calculate a thermodynamic ensemble property, you can do it by, for example, this formula here, in this case, in the canonical ensemble. So Z here is the partition function, and H is my Hamiltonian, and A is the quantity that I want to calculate the ensemble average for, and this is given by this, exactly this ensemble average. You can also calculate dynamic properties like that, for example, time correlation functions, in which you again have the partition function, the Hamiltonian, but then you have your quantity A at time 0 and your quantity B evolved at time t. And then you can also do this ensemble average. The idea behind such an ensemble average is that if you have a potential energy surface, here given in these two coordinates R1 and R2, what you need to do in order to calculate this average is sample these quantities that you want to measure in several different points in this potential energy surface, and then average over all of them, and then try to converge this average. And convergence here means that your variance is small enough that you can actually trust the average you're calculating. So what is actually more tractable to do is to use the ergodic hypothesis, in which this type of ensemble averages that I showed you just before become then a time average. And this is an equality. This is called the ergodic hypothesis. So you can calculate the same average by integrating over time here this quantity as you evolve it in time, or also the time correlation function. And this rests on the fact that your system loses memory of its initial state fast enough, so you have to go through enough time that you sample enough of phase space. So it is advantageous to do that because the potential energy surface depends on the 3n, say, -6 degrees of freedom of your system, and it's very difficult to evaluate globally. So the effort to evaluate globally goes as m to the n, where m is the number of discretizations point per degree of freedom, and n is, let's say, the number of atoms that you have. And neglecting the electronic degrees of freedom, maybe you could expand the whole potential energy surface and do this by molecular dynamics, which is actually something that you can track much easier. But then I touch already in the subject of ab initio molecular dynamics. For ab initio molecular dynamics, you can't map your whole potential energy surface before you actually do a simulation, a measurement, and so on. You have, because that effort would be extreme, right? So what you want to do in kind of ab initio molecular dynamics is to evaluate forces and energy on the fly. That means that you only want to know the forces and energies at that configuration point that you are on the potential energy surface, so that configuration of the nuclei. So this is in the heart of ab initio molecular dynamics, and for that, the reason why we call it ab initio is that we use the many-body quantum Hamiltonian, here given by this ugly expression that you might have seen already before this week. And this part here we call the electronic Hamiltonian, and what we really want to solve is the time evolution of this wave function given by this Hamiltonian here. This is the fully quantum mechanical problem. This is ideally what you would like to solve. And from this equation here, there are many routes that you can follow in order to make this equation here tractable with ab initio methods. Because if you want to solve this here, well, you hit an exponential scaling quite fast. So how to model the dynamics of electrons and nuclei from ab initio electronic structure methods. So as I said in the slide before, you start with the full-time dependent Schrödinger equation. Then you have to make a decision. Are you going to do the Born-Oppenheimer approximation or not? If you do the Born-Oppenheimer approximation, so if you decouple the degrees of freedom of your electron and nuclei, then you have to do another decision, which is, will I do classical dynamics for my nuclei or not? And if you do classical dynamics for a nuclei, you end up with methods called, for example, Born-Oppenheimer molecular dynamics or Karp-Marinello molecular dynamics. if you don't do classical dynamics for the nuclei, you have methods that are, for example, path integral molecular dynamics or these linearized semi-classical initial value representations. Now, if you don't do the Born-Oppenheimer approximation, you can also choose, even not doing the Born-Oppenheimer approximation, keeping all these non-adiabatic effects into account, you can also choose to do classical dynamics for the nuclei or not. And these are methods that I only mentioned because these are not the topic of this talk at all. I'll keep always on the Born-Oppenheimer approximation. But there are methods like Ehrenfest molecular dynamics, Tully surface hopping, Bohmian dynamics, and these new exact factorizations that Hardy-Gross actually is involved in. So here in this, this is actually very important. The cost scales massively with this arrow here, because here you're getting again back to solving the full time-dependent Schrödinger equation. And in this talk, I'll tell you a bit about Born-Oppenheimer and just a little bit about Carparnell molecular dynamics and this path integral molecular dynamics in the end. So here, it's usually classical dynamics for the nuclei, and here the nuclei are actually treated as quantum particles as well. So as I said, you need a non-the-fly calculation for energy and forces, and the way you get it from any electronic structure method is in the same way that you do, for example, geometry optimization, right? So you need to, you have the force is the minimum here of this quantity, where here I have the electronic Hamiltonian, and I solve this by solving the time-independent Schrödinger equation. So the ground state energy can actually be found by any variational method. You could do Hartree-Fock, you could do MP2, you could do DFT, or any other, and this is what we call an ab initio force. Yeah? And as you have already seen in the talk of Oliver Hoffman this week, for the calculation of the forces, you actually need to include the Poulet forces and other corrections due to the truncation of the basis sets or departure of self-consistency. And this is the equations here. So these are the forces that you want to calculate, the derivative of the energy with respect to the displacement of the nuclei, here given by this big R. And this is given by this expression here. And if you expand it all, you have all of these terms. The first term is what you call the Hellman-Feynman term, but these terms here cannot be neglected. The time scales then that you can reach when you evaluate these forces and you do this type of ab initio molecular dynamics are of hundreds of picoseconds to nanoseconds. So more than that is really out of the realm of this type of methods, and then you have to do some other type of modeling for your system. So the idea behind molecular dynamics is really simple. This is general to any type of molecular dynamics, not only ab initio ones. So you start, for example, here I give a water molecule, and you know the position and momenta for all the atoms in this molecule. So you assign them at the first step. Then the only thing you do is that you evolve numerically Newton's equations of motion for a time step, for a finite time increment, which is your time step. So you have the classical Hamiltonian here, which is given by the kinetic energy plus this potential energy. And then you have Newton's equations of motion, which anyone can derive. And these you integrate, and you only need to know the potential because then you have the force. And then you assign the new position and momenta, and then you repeat and go to the next time step and go to the next time step and so on. So this is what you do in molecular dynamics, and in ab initio molecular dynamics, of course, its potential and forces come from these ab initio methods. So the way you integrate these equations of motion is typically quite simple. So what you can think about at first is to write a Taylor expansion for your position at time t plus delta t. So the Taylor expansion is given here, where this here is the force, and then this is a higher derivative, and so on. And if you neglect these higher order terms, you have an error of your delta t time step of order delta t to the third. And these type of schemes then you could use to integrate your equations of motion, but they prove not to be stable. What is typically used is to do the forward and backward propagation of your of your position, then you sum these two expressions, and then all the odd order terms disappear. So now if you truncate at second order, you only have an error of order delta t to the fourth, and this is actually what is called the Verlet algorithm. This is how you typically integrate your equations of motion for each time step. Of course, the choice of this time step is sensitive, but the Verlet algorithm is quite good. Actually, it's the one that is implemented in the vast majority of all codes. And some good things about it is that it's symplectic. That means that it conserves volume in phase space, so dp times dr, and the form of the Hamilton's equation. So it's time reversible and so on. So about the choice of time step, you could think, well, I mean, you know, I have to evolve my system in time, and I want to reach like very, very, very long time scales. So how do I best do it? Well, I evolve my system in time with quite big time steps, and then I quickly reach many, many picoseconds. But you see, this is, for example, a simulation that I'll start here with a time step of 3 femtoseconds, so femtoseconds, right? Which is quite small. And then if I let it run, because it's an ab initio molecular dynamics, also what can happen to my system is this spontaneous dissociation of the molecule. Of course, a spontaneous dissociation is something completely unphysical, so my simulation is wrong. And the reason why the simulation is wrong is because you are not integrating correctly the equations of motion. So typically, the way you choose the time step is to look at the highest vibrational frequency of your system. And if you do a harmonic approximation, you can calculate it quite simply by just knowing the masses of the atoms that you have in your system. And then you typically choose a time step that corresponds to 1/10 of this one-tenth of the period of this height, so 1/10 of the 1/10 this highest frequency, exactly. So a question to the audience, for example, in this type of system here, do you know where the highest frequency of vibration lies? Does anyone know, more or less? Yes?
1/2 of a femtosecond? 1/2 of a femtosecond?
No. The period, you mean, or the?
Period.
No, it's roughly that. Yeah, so the period is roughly 10 to 20 femtoseconds, exactly. So the frequency will be the time step would be then 1 femtosecond or so, yeah, exactly. So this is exactly that, and typically here you have to choose exactly 1 femtosecond or a little bit less than that in order to have a good integration of the equations of motion. So the OH stretch here, which is the highest, the free OH stretch, which is the highest frequency of vibration, has a period of between 10 and 20 femtoseconds. So you go 1 over that, and that's it. So if you recall that we need, in the beginning of my talk, I said in this type of ab initio methods, you have to get the force by minimizing this energy here, which is the ground state energy. And you typically do this by doing a self-consistency procedure, right? This is what you do in density functional theory, and this is what you do in any other electronic structure method. So the question is that when you do this type of propagation of Newton's equations of motion with your nuclei, how close do you have to be to self-consistency at each time step? And this is a question that you can look at in typical simulations. So if you do a simulation of your system, for example, in an ensemble, which is the microcanonical ensemble, as Luca has already said, where the energy is conserved, you expect that energy is conserved, right, in the simulation. However, if you don't fully converge to the bottom of the self-consistent potential very tightly, you will see something like this red curve here, in which your energy is really not conserved as you go through time in the simulation. And this is because at each step you depart a little bit from your Born-Oppenheimer surface, right? However, of course, if you don't impose very tight convergency settings for your self-consistency cycle, it's cheaper because you have to do less self-consistency cycles, right? So you would like to have a method that is much cheaper in principle, and not have to pay the price to go all the way to self-consistency. And this is precisely the idea behind what Carparnello molecular dynamics was, and this was their breakthrough at the time, because doing self-consistency cycles at the time was very, very, very expensive. So what they did is that they, instead of just propagating Newton's equations of motion with the electronic Hamiltonian, they wrote instead an extended Lagrangian where they explicitly included the Kohn-Sham orbitals, which are given here by phi, in the Lagrangian, and constrain them by Lagrange multipliers, of course, that keep them orthogonal, but you add this term here that comes with an extra kinetic term that takes then a fictitious mass. So then you have coupled equations of motion for your nuclei and your orbitals, so your electrons, and you evolve all of them together at each step in your simulation. This actually means that you evolve your wave function with your system, and you don't need to do the full self-consistency at each step. In fact, this type of scheme can completely avoid the self-consistent calculation at every step, even though you need it after some steps typically. However, the fictitious mass for the electrons that you need to choose means that you don't want these type of dynamics to disturb the actual dynamics that you have in your system. So these electronic degrees of freedom have to be completely adiabatically separated from your physical nuclei. And this means that you need to put a very, 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 very small mass in order for it not to interfere with any actual mass of nuclei that you have in your simulation. However, as I explained in the beginning of the talk, if you have very, very, very small masses, it means you have very, very high frequencies of vibration, so you need to use a very, very small time step to integrate these coupled equations of motion. So you gain here, but you lose here. And nowadays, actually, since the cost for doing the self-consistency iterations has massively decreased due to computers and new algorithms that we have seen also today, some of them, people actually don't use this method that much anymore. However, it's still nice to anyway get rid of the cost of doing self-consistency cycles at each step. And other ideas that are in the literature and are very, very used for ab initio molecular dynamics are wave function extrapolations. So the idea is very simple. You want to predict the new wave function of time step Tn based on information from previous time steps. And the very naive way that is used by almost all code is to simply use the converged wave function from the previous step to start the next step instead of starting again from a superposition of free atoms densities or something like that. But there are much better schemes that are more involved, of course, in which you really extrapolate the electronic density, or in fact flavors of the density matrix, and this is just some notation. For example, if you have your Kohn-Sham orbital here, you typically expand it on basis sets, right? So these are the expansion coefficients, these are my basis sets. This can be written in matrix notation like this, and then the density matrix is given by this matrix multiplication here, and the overlap matrix is given by the overlap of my basis sets. And then with these quantities, you can choose to propagate, for example, the density matrix itself, like was proposed in this reference here, in which you predict the extrapolated density matrix at time Tn based on information from the density matrix of the previous n-2 and -1 steps. And also, which is a really, really good method is this second generation, they call it second generation Carparnello molecular dynamics, which is a way to extrapolate this contra-covariant density matrix, which is nothing more than the density matrix times the overlap matrix. And in this case, this is the formula that they use, and this is also implemented in this predictor corrector scheme that was alluded to in the first talk of this session today, in which you calculate then these coefficients for the next step based on information of previous time steps. So with these schemes, then you can accelerate again your molecular dynamics, and this can give you access to longer time scales or larger system sizes. So this is all mostly about simulations in the microcanonical ensemble where energy is conserved, but you would like maybe to get more realistic simulations. Some possibilities are to simulate conditions that are experimentally accessible, for example, control temperature or pressure, or have your nuclei not treated as classical particles. This I'll treat by the end of my talk, or enhanced sampling of the potential energy surface, as Luca has already talked about today. So I'll start by looking at the first dot here in this list. So the conditions that you can simulate, of course, microcanonical, NVE, you can do it, but you can also simulate the canonical ensemble, so NVT simulations by putting the system in contact with a heat bath, and you can simulate, for example, the NPT ensemble, which is also very interesting, where you keep pressure and temperature conserved, and in fact, any other ensemble that you want. And in this case, you have to put your system in contact with pistons or something that keeps the pressure. So in this case, what you do is really a type of computer experiment. Depending on the experiment you're trying to connect to, you should choose the relevant ensemble. And then you should equilibrate your system in that relevant ensemble and then do the measurement, which involves calculating an average in that ensemble. So first, if you want to do temperature control, for example, experiments that are typically done at constant temperatures, or situations like in biology, basically this is usually the condition. And then you can have a better sampling of conformational changes. And the idea is that if you have your system, you can involve it in a heat bath. And for the system plus heat bath, the energy is conserved. But in the system itself, the energy doesn't need to be conserved. The only thing that is kept constant is the temperature. And the way you model this is that you know that the kinetic energy follows a Maxwell-Boltzmann distribution that depends on the temperature. This is given here. And then you define the temperature of your simulation by the average kinetic energy that you have divided by here 3n, where n is the number of particles that you have. And you can also define an instantaneous temperature by looking at the instantaneous kinetic energy that you have in your system. And the idea then is that, okay, so how do I model this bath that I want to couple my system with? There are two main streams that you can model. One is based on Newtonian dynamics, so you really think about your system involved in a bath of other particles that are trying to keep the temperature constant. And then you know that the force that is exerted on the system is basically the gradient of the potential given by this whole thing. And then your heavy particle moves around like that. The other way is to take away these explicit degrees of freedom of your bath completely and do what you call a stochastic dynamics or Langevin dynamics, in which your force now is given by, in which your system moves in the same way, but not because it hits other particles, but instead because you have a friction and a random force that balance each other and control the temperature of the system. And you can do that because there's something called the fluctuation dissipation theorem that connects this random force here, the random noise, with the friction coefficient by a relationship that involves the temperature. The Langevin dynamics takes this type of random force. It's called random force because it's white noise. It means that it has no memory of past times. So this time correlation is given here by a delta function. So there are thermostats that are used in molecular dynamics that are based on these two ideas. On the first idea, which is more Newtonian dynamics, there is the Nose-Hoover thermostat. And the Nose-Hoover thermostat uses then an extended Lagrangian in which you have your original system and then you couple it to a fictitious oscillator that tries to keep the temperature, and the temperature enters here. The momenta then are damped by this fictitious oscillation, so that if it's too high, it comes back to the temperature that you want. If it's too low, it's pumped up to that temperature. And the problem with this scheme as shown in this equation here is that you have a lot of ergodicity problems because your system gets stuck in a part of phase space, and the way to overcome that is to use what is called Nose-Hoover chains. So Nose-Hoover chains, you don't attach only one fictitious oscillator, but many, all coupled to each other, and each one has a different fictitious mass, and in this way you can overcome these ergodicity problems, and this is what is usually used in codes as proposed in this reference here. For the other family of thermostats, so the stochastic ones, I will start here by telling you about a thermostat that is neither of them, which is called only temperature rescaling, just because the concept is important for later on. So temperature rescaling, or the Berenson thermostat, just rescales the velocity by a factor containing the ratio of the target temperature and the instant temperature that you have. The problem with this thermostat is, or thermostat, let's say, is that it does not sample the canonical ensemble, because it has no reason to, it just rescales velocities. And you often have an effect that is called the flying ice cube. That means that you reach the temperature that you want in your system by simply giving it translational kinetic energy and not putting any energy in your vibrational degrees of freedom. So you think you're sampling the right temperature, but you're not, because your system is just flying rigidly in space. That's a flying ice cube. Then moving away from that, the most simple stochastic idea for a thermostat is this Anderson thermostat, which was proposed in 1980. And at each end time step, you just replace the velocity of the atom by a random velocity taken from the Maxwell-Boltzmann distribution at that temperature. And this is, of course, this then samples the canonical ensemble, because this is basically the very definition of the canonical ensemble. And, but it's not very efficient, and you cannot define a conserved quantity in this system, which is not so good for you to look at the quality of your simulations. And it's very sensitive on at how many time steps you do this swap of velocities. And then came much more recently, in 2007, a thermostat that joins both ideas of this velocity rescaling and this stochastic sampling of Anderson. And this is called the stochastic velocity rescaling, which was presented by Bussi, Donadillo, and Parinello in 2007. And what you do then is that you do a temperature rescaling, but you also include a stochastic term here given by this white noise. And it turns out, if you follow this publication carefully, that this is really a very good thermostat. It is very weakly dependent on the parameters that you put to it, and you can define a pseudo-Hamiltonian, which is conserved for it, so you can also check the quality of your simulation, and it disturbs the dynamics of the system minimally, so it's indeed extremely successful. Going a bit further on this front, I mean, of course, the first idea I presented to you was actually using the Langevin equation, which is something that describes also Brownian motion and so on. And indeed, I mean, there is such a thing as a Langevin thermostat, right? You just couple these extra terms here to your original system, that friction and white noise. So friction cools it down and white noise heats it up. And then you have this relation that I showed you already before for the time correlation of the noise. And the little problems with this thermostat is that it's very sensitive on gamma. So it's very sensitive on the type of friction that you put in your system. And when your system is an ensemble of a wide range of frequencies, it's very hard to choose an optimal gamma that gives you the best thermalization. And also it disturbs the dynamics considerably, which might not be very nice for some applications that you want to see. Again, building up on that, a class of much more recent thermostats is these generalized Langevin thermostats that are called. And this was proposed, it's mainly work of Michele Ceriotti, but also with Giovanni Bussi and Michele Parinello. And they are extremely flexible thermostats that basically model your system as a Markovian process in a high-dimensional space. So now you don't have only your physical system plus this friction and white noise, but you have fictitious extra degrees of freedom that are here given by S. And you can write this generalized Langevin equation in this higher dimensional space here, where now you also have friction and white noise, but this is now controlled by these matrices A and B here. And then you can integrate out these fictitious degrees of freedom, and then you have the actual equations of motion for your physical system. But when you do that, you do not have anymore a white noise. You have what we call a colored noise in the memory kernel. Having a colored noise simply means that the time correlation of your noise is now not a delta function, but is given by this time-dependent kernel here, which is time-dependent or frequency-dependent. So it has a spectrum in frequency space. And with these thermostats, what you need to do, what is a little bit more involved, is that they depend on a lot of parameters, depending on how many S degrees of freedom you choose to couple of your system to your system. And then you have to input these matrices, so this A matrix and the C matrix, which is the covariance matrix, which is also connected to that B matrix, that is the drift that is the matrix that I showed in the slide before. A is called the drift matrix. But these parameters are already parameterized, and you can download them from these. Sorry, it's actually this link here. That other link doesn't work anymore, so this is the correct link. And then you can simply use these thermostats for any situation that you want. And because of this flexibility, they can work very well for systems with a very wide range of frequencies. It optimally thermalizes all degrees of freedom at the same time. And you can also play with them in cases where you break this fluctuation dissipation theorem, so you don't have this relationship between friction and noise anymore. And then you can model very, very exotic things like nuclear quantum effects for your nuclei, or accelerate some types of simulations that you'll see later on. And on this front, last but not least, I mean, you can also do pressure control. You simply need to define your pressure here, which can be given as this expression that I show here above. This is the kinetic energy, and this chi here is given by this formula, which is basically the volume times the stress tensor, which is something that you can calculate in your simulations as well. And having these, you can input that into pressure control schemes, and these are very similar to these thermostat schemes that I just showed to you. So there is pressure rescaling as well. There is extended Lagrangian that controls pressure. That is the Sparinello-Raman work here. Or there's also the stochastic pressure rescaling, which is very similar to that temperature pressure rescaling that is work of Giovanni Bussi and Michele Farinello, also from 2009. So these are things that are also around. And in that case, you sample an ensemble which conserves the enthalpy and the pressure. And if you want to conserve also the temperature, then you couple the system to these barostats here, but also to thermostats. So you couple to both things, and then you have temperature and pressure control. So this is typically how you do the simulation. And now this is all I wanted to talk about general molecular dynamics, especially with classical nuclei. And I'll take a little bit of time now to tell you about when do you need to consider nuclear quantum effects for your nuclei. So typically, nuclei are quite heavy particles, so they are quite classical. However, the way to look at them is really to look at this quantity that Luca Ghiringhelli already showed in his talk, which is called the de Broglie wavelength of your atom. And the de Broglie wavelength is here given by this relation where you see the mass of the particle and the temperature here in the denominator. So typically the rule of thumb is that if this quantity is much larger than a typical interparticle spacing of your system, then that happens when you have low mass or low temperature, nuclear quantum effects will play a role. And that's because this quantity here gives you an idea of the extent of your wave function, if you would have one. So if the extent of wave function is more than your interparticle spacing, then nuclear quantum effects might play a role. Now, if it's the other way around, that this quantity is much smaller than your interparticle spacing, then you don't need to care about that too much, and that happens with high mass and high temperatures, and then you have classical Boltzmann statistics, and everything in classical thermodynamics holds. I show you here some estimates for this quantity for different particles at different temperatures. So the electron at 300 K has lambda of 43.03 angstroms. So as we all know, electrons are quite quantum no matter what temperature you look at them. And this is a good indicator then. But hydrogens at 300 K have this lambda here at about 1 angstrom. So 1 angstrom is actually a very relevant length scale for any system. So hydrogens are quite quantum even at room temperature. And here are other atoms. I just want to make a point that as you lower temperature, all atoms become quite quantum, right? I mean, because then you have even for copper, you have 0.7 angstroms as a lambda. The other way to look at it is how far from equipartition of energy you are. So if you look at your frequencies of vibration and divide it by kBt, if this number is much larger than 1, then those vibrations will be dominated by 0-point energy, and the equipartition of energy as given in classical Boltzmann statistics doesn't hold. I show you just a little bit of an example of how this could impact our lives. You know that the average of the kinetic energy classically is just given by 3n kT over 2. That's, again, equipartition. But quantum mechanically, this is not so. In fact, quantum mechanically, you can generally not calculate the analytical expression for this average, but for a harmonic oscillator, you actually can. And for a harmonic oscillator, you can write this expression here for your average kinetic energy in the canonical ensemble. And you see here that it depends on the mass, and it depends on the square root of the mass here in this prefactor. So the kinetic energy is something, for example, that controls the pH or the pKa of things. So we all know that water that we drink has a pH of 7, and this is good. But you can also measure, so this is taken from a book, you can also measure the pH of DOH, D2O, T2O, and they follow, if you plot here on this plot over 1 over square root of mass of the hydrogen atom, basically, you see that they follow on a line, and if you consider the classical limit to be the limit when you have infinite mass for these atoms, you can extrapolate this curve here and see when it crosses 0, and then you have the pH of what would be classical water, and that would be basically 8.5 or so. Many things in your body depends on the pH of water being 7, and if you actually would drink classical water, you would die. And we know that because there were some experiments very long ago, and this is a very disturbing paper to read, but it's physiological effects of deuterating a dog. And this is from 1961. And they say that, well, they tried to deuterate dogs and they eventually died. And they also did in mice and they eventually died as well. So if you really drink deuterated water, because of the pH effect, you would die. So, for example, this is, quantum nature of nuclei is important for your day-to-day life. Yeah? So the way you do path integral molecular dynamics, the way you include, these nuclear quantum effects in your actual simulations is, for example, to do path integral molecular dynamics. And this type of simulation is exploiting a relationship between the statistical properties of a real quantum system and that of a classical ring polymer. So the thing is that you can show that the partition function, the canonical partition function for this quantum system given by this wave function psi and this Hamiltonian operator is the same. It's exactly the same partition function of a classical ring polymer with n beads when the number of beads goes to infinity. And this partition function is then calculated with respect to this Hamiltonian Hn that I will show you in a second. So you can show this equality, and this equality is exact. So this means that you can map your quantum system into a classical one. And you can show this by doing Wick rotation from real to imaginary time, where imaginary time here is I beta h. And you see that this canonical density matrix that I just show you here maps to the quantum mechanical time propagator if you are on imaginary time. So quantum statistical mechanics is basically the same as propagation in imaginary time. Now, I won't go through the whole derivation of that, of course, here, because there is no time. But I can give you references where it's done. It's actually not hard at all to do this derivation. And what happens in the end is that you go from this classical system that was given by this Hamiltonian here to a quantum system that is now given by this Hamiltonian Hn that I alluded to in the slides before. And you see that this Hamiltonian is really a Hamiltonian of a ring polymer, in which you have the kinetic energy here, you have the potential energy here, and you have this, what we call the kinetic term, which is the spring term that connects two beads of a ring polymer, and H bar, which is the signature of quantumness, appears in this omega n, which is the strength of the springs between each bead. In this case, it's a bit difficult to imagine, but actually imaginary time goes around, the loops around the ring polymer, so each bead is actually a slice in imaginary time. But what you actually do in simulations is that you just need to include several replicas of your system. So each bead is a replica of your system, and they are connected by these springs that you know how to calculate analytically, okay? And this ring polymer has some interesting properties. For example, the radius of duration of this ring polymer is connected to that lambda that I showed you in some slides before, so the thermal de Broglie wavelength of your system. And so that means that the spread of this ring polymer has to do with the spread of your wave function. Now, the way you do the simulations is that each bead of this ring polymers evolves at a temperature n times t, where n is the number of beads in your ring polymer, and t is the temperature that you want to sample in your canonical ensemble. And n is determined by how quantum the problem is. So, of course, you cannot make n goes to infinity because this you cannot simulate, but you can see how many replicas, how many beads in these ring polymers you need by looking again at the maximum frequency of vibration of your system. And n has to be bigger than h bar omega max over kt, right? Beta is 1 over kt. And typically this gives you a value between 10 and 100 for typical systems in typical temperatures. Of course, if you go very, very low in temperature, you need exponentially more beads as you go down. So I just show you here what happens if you have many atoms, not just one atom as I had in the slide before. This is how the Hamiltonian look. And if you want to think about how your simulation actually looks like, you really, like if you take that molecule again, you just have lots of replicas of them, and you evolve them separately and then join them together by these spring terms, okay? So the effort of actually performing the simulation is just the number of replicas times your classical simulation. And these replicas are trivially parallelizable, so you actually just need to have enough processors, and you can have this simulation at the same cost as a simulation with classical nuclei. And I must say there have been several developments recently in the literature where that make you need even less replicas of your nuclei, of your system at any given temperature, so that nowadays one can really perform this type of simulations routinely if your problem calls for it, if you need. And the way you do it, I now will do a little bit of advertisement of something here, I guess, but the one way you can do it is through this code that I co-develop. It's actually a code of Michele Ceriotti, who will be here next week. So if you want to talk to him too about it, he will be there. If you do the exercise this afternoon, you will see this code connected to FHI Ames. And this code is called IPI, and it's a wrapper code. So it's based on the idea that you decouple the ionic equations of motion from your actual evaluation of the electronic structure. Because the molecular dynamics, or this path integral molecular dynamics engine, doesn't need to know much about the electronic structure. It, in fact, just needs to know the forces, right? So it needs to know the forces, and then it needs to say what are the next positions that my electronic structure code needs to calculate. And it is actually, the same idea would work for other ion motions that are also decoupled, like geometry optimizers or any type of other movement of ions that you can imagine. And it's often useful to use the electronic structure as a simple driver and to have this external engine control it, because then you can unify the implementation of the several schemes basically only outside your electronic structure code. So this is exactly the idea behind IPI. So if you want to start your electronic structure code, for example, FHI-AIMS, you give the parameters for the electronic structure calculation, the code will initialize everything that it needs to initialize. Then it will receive the positions and the cell parameters from this other code, IPI. Then it will compute energy and forces, and then it will give back the energy forces, the stress tensor, and maybe other electronic properties if you want to keep track of them. The way IPI does this communication is through internet sockets. So it's a Python code which works through Unix or internet sockets with your code, and this makes it quite easy then to use in different machines or supercomputers and so on. And it's interfaced to FHI-AIMS, CP2K, Quantum Espresso, LAMPS, DFTB+, and the list of codes is interfaced to only grows. So you can use it with really many codes. You can download it from this page. This is the publication of the first release of the code. As I said, it's mainly work of Michele Ceriotti. And now the team has expanded a lot. And the way you do that, this is again now, I have again my electronic structure code here, but now I have the IPI server, and I don't need to have only one instance of my electronic structure code connected to it, but many, many, many. Let's say I need to do this path integral molecular dynamics. I can have each replica of my system in a different instance of my electronic structure code. Or if I want to do parallel tempering molecular dynamics, I can also do the same. And then I have several clients. Also, I could, for example, to do thermodynamic integrations, I could put different codes because I want different potentials, a classical potential and an electronic structure one. I can have two clients that have that are different here, and then IPI knows where the forces is coming from and couples it together inside. So IPI does all of this evolution of the nuclei, output the properties, and controls this distribution of these replicas of your systems over the many clients of your code. As I said, for path integral molecular dynamics, you really get almost linear scaling when you have several replicas because you can just separate these replicas almost analytically. The deviation is just because you need to wait for these self-consistent cycles in each replica. And there is a new release coming out in which you can do a bunch of things connected to FHI-AIMS, for example, all the time in this code. So this is a list here. This is the main developer. You'll see him next week. And this is the rest of the team. These are the main people doing that. And you will see how to use it this afternoon as well. A few examples just to close of what you can do with that. For example, something we published recently is to calculate free energies of molecular crystals, fully ab initio. In this case, you need to do a series of thermodynamic integrations. So here, for example, if I want to know the cohesive energy of a crystal, in this case it was a molecular crystal, I can calculate it at the potential energy surface. This is no problem. I calculate the energy of this, divide by n, and then calculate the energy of the molecule and get it. Then I can easily also do an estimation of the classical harmonic free energy of this system because it's based on an approximation of harmonic oscillators. This has an analytical expression. Then if I want to calculate anharmonic terms, this is more complicated. As Luca said earlier today, you can do something called a thermodynamic integration, and this can come in several flavors. The flavor we did here is between a Debye crystal, that means a harmonic crystal, up to a crystal given by a force field potential. So you write your potential like this here, and then you do this thermodynamic integration where you vary the lambda parameter from 0 to 1. And then you calculate this average that is shown here, which is the difference in potentials. And this you can really do if you use a force field potential here, but this is a very costly calculation that you need to use many integration points for it to be done. So you can actually not do it ab initio, but wait a moment. And then if you have the classical anharmonic free energies, you can also add to that the fact that your nuclei are quantum particles, and you can do that by doing another type of thermodynamic integration, which is called a mass thermodynamic integration. This means that you're assuming that the classical limit is the limit given when you have infinite mass of all the particles in your system, which is very well defined. And m0 here is the actual physical mass. K is the quantum mechanical kinetic energy, which you can measure through these path integral molecular dynamics simulations, and you just need to do that. Now, if you want to do it ab initio, as I said, you cannot do this step, going to classical harmonic to classical anharmonic, but what you can do is to do yet another thermodynamic integration that takes you from this point here in the force field to the DFT one. So you write your potential as shown here above, and you can calculate this average, and then you get this point here in this diagram, and then you can calculate the quantum contributions with DFT. I just want to say that this was all done with electronic structure codes and force field codes connected to IPy, so this is the type of thing you can do. And you can also calculate, for example, diffusion coefficients. In this case, we studied a wire of water molecules here, and we were interested in the diffusion coefficients of protons and OH minuses in these wires. And this is something given by the Fourier transform of the velocity autocorrelation. This is also something you can calculate with molecular dynamics. And then you get different values for diffusion coefficients here, and this is simulations with classical nuclei. They depend a lot on what type of functional you use in your simulation. So this is Bilip including van der Waals for the proton diffusion, and Bilip not including van der Waals. And you see that the diffusion coefficient is basically double when including van der Waals here. And then you can also look at the OH minus diffusion coefficient. And then you can look what happens when you include nuclear quantum effects in your simulation. And you see that for these cases where, for Bilip, for example, that had a very low diffusion coefficient, it's almost doubled. For OH minus, it has some effect. And here, for the proton in Bilip plus van der Waals, we see basically no effect. And you can actually understand this behavior by looking at these free energy surfaces. This is also something that comes out of molecular dynamics simulation that you can calculate. And you can see that if you look at Bilip without van der Waals, and you plot here this oxygen-oxygen distance versus this proton transfer coordinate, which is given by the difference in distances between these two OH groups. This is what's given here. You have a barrier for the transfer of this proton when you are doing classical nuclei, but this barrier completely disappears when you're doing quantum nuclei. And then you can see what happens when you include van der Waals. Basically, because your H bonds are stronger, your oxygens are closer together, so the oxygen-oxygen distance is a bit shorter than it was here. And the barrier, even if you don't include the quantum nature of the nuclei, is much lower. So this process is already thermally activated at room temperature. So when you include quantum nature of the nuclei, which is this plot here below, this barrier again completely disappears, but it was already not anymore the rate limiting step for this diffusion. So the diffusion coefficient doesn't change. And if you look at OH minus, the picture holds because you have, even classically, you have a higher barrier if you use the same functional than you had for H plus. And when you do nuclear quantum effects, this barrier completely disappears and you have a much faster diffusion. So this is all I wanted to say. And here are some references for books that you can look at to look at these methods if you are more curious about that. And also this afternoon, there's this exercise session. So thank you very much.